part of any electronic device. In this video, we'll explore the inner workings and applications of the diode in great detail. Basically, a diode is a one-way valve for electricity. Let's take a look at the internal structure of a diode. The diode is made of a semiconductor such as silicon. Pure silicon does not have any free electrons, but the silicon used here is not pure. One part is doped with N-type impurity and the other part is doped with P-type impurity. So at the N side of the diode, we will have free electrons, and at the P side, we will have vacant positions for electrons. Something very interesting happens at the P-N junction of the diode. The abundant electrons on the N side have a natural tendency to migrate to the holes that are available on the P side. So the P side boundary is slightly negatively charged, and the N side boundary is slightly positively charged. You can see the depletion region that is created. The resulting electric field will oppose any further natural migration of electrons. In short, it builds a potential barrier for electron flow. If you apply an external power source across the diode as shown, the power source will attract the electrons and holes. Electricity flow is impossible in this case. This condition is known as reverse bias of the diode. You can see that the width of the depletion region increases here. However, if you connect a positive terminal of the power source to the P side of the diode, the situation is quite different. Assume that the power source has enough voltage to overcome the barrier potential. You can immediately see that the electrons will be pushed away by the negative terminal. When the electrons cross the potential barrier, they will be drained of energy and will easily occupy the holes in the P region. But due to the attraction of the positive terminal, these electrons can now jump through the holes nearby in the P region and flow through the external circuit. This is known as the forward biasing of a diode. Simply put, a diode acts like a one-way valve for the flow of electricity. Now, let's vary the input voltage and study the diode's response to it. In reverse voltage, as explained, you can observe a negligible electricity flow. In the forward condition up to 0.7 volts, you will find a negligible electricity flow. But right after crossing this barrier potential value, there will be a steep increase in the current flow. However, you can note that voltage across the diode does not go much higher than 0.7 volts, even with high input voltage. This is due to a forward biased condition. The diode offers very low resistance against the current flow. At the reverse biased side, applying a very high voltage will damage normal diodes and result in a high current flow. The one-way electricity flow that is characteristic of the diode leads to interesting applications like a bridge rectifier.
That's
During
the
the
way
positive
rectifier
half, the circuit will conduct as shown. The other two diodes will be in a reversed biased state. During the negative half, the reverse will be the case. So we will get the same current flow direction at the output. We can further smooth this output by introducing a capacitive filter and regulator. Our educational service is made possible by the support of our patrons. Your support at patreon.com is greatly appreciated. Thank you.
Alright, and here's one real quick one on
Too much
LED.
voltage, they will be destroyed. And so we use a resistor to protect the LED. This is an LED, or light emitting diode. When we energize it, it produces light. We get them in many different colors. Inside is a tiny piece of semiconductor material. The semiconductor is just two special materials joined together. And this emits light as photons. A battery pushes electrons around the circuit, and inside the semiconductor, the electrons are jumping from one layer to another. As they make the jump, they will release a photon particle. The photon travels in a wave-like pattern. Different materials produce shorter or longer photon waves. The length of the wave determines the color of the light produced. The color is not because of the case. Even this transparent LED produces colored light. If we apply too much voltage, they will be destroyed. And so we use a resistor to protect the LED. This is an LED, or light emitting diode.
And finally, let me just go to, if any of you had a chance to look at this, but this was my kind of intro to just the philosophy of the lab in general. So we'll have labs typically will be due every 2 weeks. If we don't have enough time to finish today with 2 hours, following the quiz shouldn't be more than half an hour, 45 minutes, so you'd still have another hour and a half if you needed to collect more data next time. But
You want scantrons for the quizzes?
no, I don't think you need that.
Okay.
I think you can mark it down that one. That should be fine. So I'll be looking for hard copies of the lab rather than virtual copies. The first one I'm going to have the fewer points. So we talked about how LEDs work. What's different about the labs? Essentially, even though I know I've kind of constrained you a little bit here, what I really want you to do is think outside the box. And what we've done in previous labs is just fill out a bunch of boxes and fill some things in. And so it's kind of robotic almost, what we've been doing up until now. But the part of the purpose of this capstone class is to get you ready for the upper division and for thinking independently, making your own decisions. And so we're not going to have any pre-labs for this. We're just going to basically be focusing on, what do you think were the biggest sources of error? How much data do you need to gather? How are you going to write this up? If you were trying to convince, say, if you were writing this for a research paper, how convincing could you be that what you've measured is actually viable? And so the lab write-ups will be more intensive in terms of things that I'd like to include in the lab. Have things like, here, let me just pull out sample lab. It'd be nice to have a brief history of the subject. Theory. And no handwritten equations, text equations. Some kind of a discussion of the setup. That includes a photograph of the device. And then in the analysis, be sure to show error bars in your graphs. And also also, here, let me just circle this, how were the error bars calculated? I see a lot of error bars, you know, they're great. I need to know how they were calculated. So sample calculations on how they were calculated. Qualitative and quantitative error and in this, I'd like you to have some kind of a discussion of what we could call error propagation. In other words, if we're going back to this example here, we could say, well, if I chose this point rather than that point, how big of an error does that create in Planck's constant when I compute the slope? And so your error bars then could indicate the limits of the difference that was chosen by that. But then that would result in a new computed slope that would have a different final result. And so we could see then how did that error propagate. Another example of error propagation which could work for this lab is what happens if the fees aren't all the same. And we might have, and so you can assume, I think for this lab, somewhere in there it was saying that because of impurities in the material and that sort of thing, you might get a little bit of a spread in the wavelengths, maybe plus or minus 5%. And so you can make some kind of an assumption there and then follow that through with how does that affect the final results. In other words, it's giving you a little more of a feeling for what the bounds are of your final result. And so we should also include standard deviation. But supplement that with a little bit of error propagation. Okay, what else in here is worth talking about? Here, how LEDs work. This is a sample problem that did it the same way my son did it, by assuming this was 0. Okay, and this is right out of Halliday and Resnick. And what was he getting? 35, 40% error. So there's definitely some value here that's non-zero for that energy that's lost. That it wasn't 100% efficient as the electron's energy at the top turned into photon energy at the bottom. Some energy was lost. How was it lost? You could speculate on that in your qualitative part of this. You could speculate on, and it's okay if you're wrong. You know, if you just make it a speculation, this might be because such and such, and because of the molecular structure, there was an interaction in this p-n junction region which did such and such, and that's great. You know, just try to stretch your mind a little bit and think deeper about what it is that is happening in the lab and what could be affecting your results. Because if you're trying to publish a paper, you're going to be getting attacked. You know, the reviewers are going to say, what about this? What about that? What about that? And so try to think in those terms where you can get the upper hand on potential problems so that you're addressing them yourself. And then we have variations in because of impurities in the substance, we have variations in the wavelength. Okay, here's a comparison of the variation in the wavelength for a laser versus an LED. Over here. You can see, look at how wide that peak is for the LED. For the laser, it's pretty much dead on. It's all the same frequency. And so, and when you talk about a few parts in a billion for the impurities, you can have variations on that. And I think that's going to be natural, that you could have, say, plus or minus 5%. And so that's going to affect your horizontal error bars here. The variations that are associated with typical values that in the spread of the wavelength is also going to affect your slope. And so you've got two sources that I can think of vertical. One is that this thing isn't intersecting right where the extrapolation should be. There's some weird reason for that little hump in the curve. And the second one is that not all of these phis are the same. So if not all the phis are the same, then you're kind of looking at a variation here that could look like delta phi over QE for your up and down motion, where delta phi could equal phi average minus phi I. So this would be like delta phi 2 would be the average phi for all of them, because if they were all the same, then you'd intersect to the same value. But if they're different, then there'll be a spread from the average, and that'll give rise to a vertical error bar. Okay, and then finally here, error propagation, and then conclusion. Okay, and so we've got a couple of sample write-ups here from previous semesters. In the theory, it's nice if you can have pictures. I thought that's kind of a nice picture. This original one was in color, but if you can find things like that, that'll look really good. So I went longer than I was going to, but there were a lot of things to cover. So are there any questions? At least this lab should be relatively easy to collect the data. And so just try to be careful. And remember, when the light goes out, that's when you really start looking at the microamps over here. And then you back off just a little more, because you might have like maybe 2 or 1 microamp when this thing looks like it's going out. And then don't necessarily expect, at least from experience, that the infrared one, that would be the one with the biggest value for 1 over lambda. The infrared one may be off. And so you could try calculating your slope with and without the infrared one. And you might get a more accurate value without it. Okay, so you'll always have a sample setup you can refer to here. Mark.
I have a couple questions in the summary. So you want them to, when the 7 different LEDs, they should be plotting voltages at, or voltage and current at different voltages. That's
right. So you should have 7 of these.
okay. And you also
and
want
that'll come together for some. Now it doesn't have to look exactly like this. And if you think of a better way of plotting this up, that's okay too. When Clay did this, he plotted voltage versus frequency, which is basically the same thing. But when he plotted voltage versus something else, and he did each of the individual calculations, assuming phi was 0, he got huge error bars, and so I wouldn't plot that. I wouldn't try to calculate individual values for H for each data point. Now, you should get values for H that are in the right ballpark. If you want to just take one of your points, do a quick little calculation and see that you're getting something on the order of maybe 4 to 7 times 10 to the minus 34, then that'll show you that your units are correct before you get going with the rest of the analysis. But you wouldn't want to calculate Planck's constant just from one single measure.
And then they also want to have the stopping or activation voltage for the
Well,
LEDs?
the activation voltages come from these plots.
Okay, what I
So
mean.
those are the values of V that
Okay.
go onto your main plot.
Okay.
Are there any questions? Any points of confusion? Or anything? And then if you're not sure, just let me know and I can take a look at it with you and see how it's looking.
So